Thank you everyone for joining today. As we get started here, I just wanted to tell you that we're going to be discussing the basics of dust collection system design. This is just one of many educational webinars for engineers. My name is Ashley Zook and I'm the National Channel Manager here at Donaldson Company. I work with national engineering firms across the United States, and one of the ways that I help is through webinars like this one and scheduling in-person lunch and learns. The purpose of today's webinar is to discuss the basic of dust, fume, and mist collection, why it's important, and what we are collecting in the common industries we work with. Discuss the 4 primary components of system design, including the hoods, the ducts, the collectors, and the fans, including some of the common mistakes that we see. And then we'll finish up with the Q&A session. Just a heads up, it takes years of education and experience to become an expert in system design. We're going to give you a brief overview of the basics today. In case anyone here isn't familiar with Donaldson Company, we have been solving customers' complex filtration challenges for over 100 years. We were founded in 1915 by Frank Donaldson Sr., who invented the world's first filter for tractor engine. Today, we are one of the largest providers of unique filtration technology, and we excel at producing high-quality filters and parts. We pride ourselves in having a global reach with a local touch. Our world headquarters is here in Bloomington, Minnesota, and we have 55 manufacturing facilities and 21 distribution centers around the globe. Before I introduce Jack, I wanted to quickly show you how you can engage with us. As you think of questions throughout the webinar, please type them in the chat box and Jack will answer them towards the end of our session. If you need to jump off early, don't worry, I'll be following up with an email. And then during the webinar, Jack will ask you questions and you can respond by clicking the thumbs up and thumbs down by clicking on the little face icon at the bottom of the screen. And with that, I am pleased to introduce our featured speaker, Jack Holtz. He has been working with Donaldson Company for 29 years. During this time, he has been involved with engineering, sales, and support of industrial air filtration. He lives in Delafield, Wisconsin, and he is the territory manager for the southern Wisconsin area. Prior to Donaldson, he worked 6 years selling and designing marine propulsion systems for commercial and naval vessels, and he holds his bachelor's degree from the University of Wisconsin-Madison. And with that, Jack, you can take it away.
Thank you, Ashley. Greetings, everyone. We would like to start out by asking about your experience with designing dust collection systems. Please use the chat box and type in the letter that best aligns with your level of experience.
All right, they're coming in here. It looks like we had a lot of C's, a couple A's, a couple E's. Yeah, we got a little bit of everything.
Thank you for your responses. Again, it's helpful for us to know the experience level of this group. Okay, let's start with the basics. For those of you who are new to dust collection system design, many different types of industrial processes generate dust, fume, and mist. You'll see dust collectors helping to keep employees safe when working with metals and machining processes like welding, wet machining, abrasive blasting, and grinding. Dust collectors can be found installed in grain elevators, soybean and seed processing plants, and flour mills. Large volumes of hard abrasive dust particles are typical in most mining and mineral processing related applications such as rail and truck dumps, crushers, conveyor belt transfer points, and silo filling. A lot of dust is generated during woodworking, from school wood shops to cabinet makers to lumber milling. Automotive is a huge market for dust collection, and even more so with the emergence of electrical vehicle battery mining, manufacturing, and recycling. Food processing industries move a variety of products: grain, sugar, flour, dairy, cocoa, cereal, and spices. And dust collection is needed in applications such as bulk and material handling, conveying, packaging, and silo and bin venting. Industrial processing often generates the type of dust that generates and requires control, such as chemicals, glass, insulation, plastics, and textiles. Pharmaceutical manufacturing can produce toxic dust, which are critical to control during processes such as crushing, mixing, blending, and coating. There are a lot of important reasons to control dust, fume, and mist, including safety concerns and hazard, improving air quality for employees, exposure control, reduce potential dust and breathing zone of workers operating the process, environmental concerns, EPA standards for outdoor, exhausted environmental air quality, and other outlet emission requirements, and general cleanliness, concerns about overall cleanliness of the facility. Here's a diagram of a typical dust collection system. A blower or fan creates an airflow which is used to capture dirty air with a hood and then convey the material through a series of ducts to a dust collector. Here, the contaminant is separated out and clean air passes through a filter media to the fan where it is discharged to atmosphere. It's very typical for these types of systems to have the fan on the clean air side, so you're drawing the air through the negative of the whole system through the filter. If one component is poorly designed, the whole system is affected. Here's a real example of a dust collection system. This one is for a robotic weld cell. You can see the four elements: the fan at the top with a silencer for noise reduction, the dust collector, this one happens to be a cartridge collector, which we will get into later, the ductwork, and the hood. When we design a system, there are a lot of factors that are to be considered. The publication here is the Industrial Ventilation Guide, which is an indispensable resource for proper system design. The vent manual is written by the American Conference of Governmental Industrial Hygienists, or the ACGIH. It is a nonprofit scientific organization that advances occupational and environmental health. We offer multiple courses throughout the year on system design using the vent guide as a textbook. I've attended multiple courses myself over the years. The ACGIH guidelines are considered by most in the industry, including OSHA, as a standard for proper ventilation design. Things that we consider when designing a system include the material being collected. This includes the specific properties of the dust being collected. I'll talk more about that in a moment. The application being utilized, the process conditions, such as, is it humid? Do workers use personal fans? Does the plant or area have conditioned air? What are the hours of operation? Will the system be used continuously or intermittently? What is the total airflow requirement? What location or environmental restrictions exist? Do they have compressed air available? Does the collector need to be located indoors or outdoors? Another, has the dust been tested for combustion and flammability? If it is, what NFPA standards apply? And finally, does the plant have expansion needs that we should consider when first designing the system? As you can see, there are a lot that goes into designing a system, probably more than most people realize. When we think about collecting dust contaminant, there are some important characteristics to consider, which help us determine the type of collector and the filter media to use. As you can see, the dust comes in various different shapes and sizes. Bulk density, how heavy is it? Is it abrasive? Is it conglomerative or fibrous, meaning does it stick together? Is it hygroscopic, meaning does it retain moisture? What is the chemical composition, meaning what is it made out of? Is it corrosive, toxic, or even explosive? And speaking of explosiveness, it's important to know that some dust and fumes may present a combustible risk. If the dust or fume is combustible and it mixes with air, like the airflow coming into a dust collector, and an ignition source, it could result in a fire. And if you add in the dispersion of the dust, which occurs frequently in pulse cleaning collectors, you could get a flash fire. And then if you add in the confinement of the dust, such as the dust collector housing, you could even get an explosion. I wish we could spend more time on this, but it's really a complex issue. For now, it's important to know that if dust or fume is combustible, it's important design consideration. Typically, we need to know things like who is the process owner, who is the AHJ, and is there any information from their DHA? We have a team of combustible experts who can help you. So if this is a topic that interests you, make sure to reach out. There are many different terms and calculations to learn when it comes to designing a system, but I wanted to go over just a few basic ones. The first being airflow. It is the total volume of air being processed in 1 minute. It is expressed in cubic feet per minute, or CFM. You can calculate airflow by taking the velocity of the air, or the linear speed, and multiply it by the duct area or cross-sectional area of the duct. Looking at the formula, Q is the same as airflow. V is the velocity, and A is the area. It's the most important calculation when it comes to dust collection design, and one that I use all the time. There are many different types of velocities involved in dust collection, so let me show you a few of them by using the following diagram. Duct velocity is the speed of the air flowing through a duct. Capture velocity is the speed of air at the hood or area of generation. Face velocity is similar, but is the average velocity of the airflow crossing the entry plane of the hood. Filtration velocity is the speed of the airstream as it enters and passes through the filter. This is also referred to as AMR, or air to media ratio, and for those of you who are more seasoned individuals, air to cloth. Institutional velocity is the speed of the air between the filters. And finally, can velocity could be another important factor to consider when it deals with airspeed in an enclosure. I already mentioned about air to media ratio, or AMR. It's the same as filtration velocity. It's calculated by taking the actual CFM and dividing it by the total filter area. It's expressed as a ratio, such as 6:1. In this case, it represents 6 cubic feet of air flow for every 1 cubic foot of filter media. And the last basic term I wanted to talk about is static pressure. It's resistance of airflow in a system from things like collector, the filters in the collector, which will create more resistance when they're dirty, the hoods, and the ducts. So static pressure is a critical factor to take in consideration when designing a system. Now let's get into the 4 main system components: hoods, ducts, collectors, and fans. A hood design is a critical component of a system design, which will allow for the collection of contaminant or fugitive dust. A well-designed hood is going to minimize the amount of airflow that's required to effectively capture and control the contaminant where it is released, while minimizing the energy required to do so. With this, when it comes to assessing an existing system, a few common mistakes I see are the wrong style of hood being used, the hood is not located in an effective position, or you have inadequate airflow at the hood. A closed capturing hood is generally the most effective method of capturing material. There are 5 main types of capturing hood. They are presented in order of increasing effectiveness, but also increasing fabrication cost. They are the raw edge hood, the flanged or tapered hood, the bell mouth hood, and the slotted hood. Regardless of the style of hood, they must be positioned properly relative to the point where the contaminant is emitted. Remember, the first objective in a hood design is to minimize the air volume required to maintain capture efficiency. To minimize air volume, the hood must be close as possible to the capture point without disrupting the process. Hoods simply cannot just reach out to control contaminants that are far from the inlet. Consider, for example, a vacuum cleaner in your own home. To pick up debris effectively from the surface, the vacuum head must be close to the contaminant. A hood positioned twice the distance from a contaminant emission point rather than at the capture point will require the draw of approximately 4 times more air to produce the same capture efficiency. And more air means larger collector equipment, larger ducts, larger fan, higher horsepower, all of which adds to capital and operational costs. When determining the required airflow at the hood, the main design factor is capture velocity. To give you a few examples, thermal generated capture velocity is typically about 100 to 250 feet per minute. Wood dust is typically about 150 to 500 feet per minute, and rock dust, which tends to be heavier, is typically around 400 to 500 feet per minute. Too much airflow at the hood or pickup point may mean you're picking up good product rather than just nuisance dust. It could also increase your risk of capturing unwanted material like sparks or embers. And since more energy is required to move more air volume, it could lead to higher than expected operational cost. Insufficient airflow at the hood could result in additional housekeeping requirements, and depending on the dust may lead to an increased risk of employee exposure.
Hey, Jack, sorry to interrupt you. I'm guessing you probably need a drink of water right now. So as he does that, I just wanted to remind you that you can chat in your questions as you think of them, and Jack will address them at the end of the session. Back to you, Jack.
Thank you, Ashley. Once we design a proper hood to capture the contaminant, the goal is to move the particulate to a filtration system throughout the series of ducts. A proper designed duct system pull the minimum airflow required at the hood, maintain velocities required to transport material through the duct throughout dropout to the collector. One needs to be able to do all this utilizing the least amount of energy as possible and minimizing any wear or tear on duct components. A few common mistakes that we see when it comes to duct design are the incorrect type of ducting that is being used, the incorrect duct size or fitting being used, and the duct system not being balanced correctly. Minimum duct velocity is the lowest velocity where all contaminant will be transported through the duct system. Typically, we size the ductwork to maintain a minimum velocities between 2,500 to 5,000 feet per minute in the ductwork. If the dust is combustible, NFPA requires a minimum conveying velocity of about 4,000 to 4,500 feet per minute, depending on the material being collected. If the duct velocity is too low, dust could settle out within the ducts and could cause problems, especially if the duct is combustible or flammable. If the duct velocity is too high, it could create safety concerns such as sparks or abrasion, as well as demanding higher energy than needed. A little advice when it comes to choosing the right duct type to use. Rectangular duct is used when moving air only. It is not recommended to be used in industrial applications because dust settles out in the corners and can create uneven airflow. When specifying industrial duct systems, make sure to specify heavy-duty round industrial ductwork. Most dust collection applications use either Class 2, 3, or 4 ductwork depending on the design due to SMACNA standards. Typically, the higher the class rating of the ductwork, the heavier the gauge. It is best practice not to use spiral duct at all in industrial applications because it could lead to higher static resistance, leakage, structural integrity issues, and dropout of material. Regarding the use of flex duct or flexible duct, it should be of smooth interior wall construction and to be used at a minimum, basically near the hooding process, if needed. If used, make sure there are no chemical reactions related to the materials being captured. Lastly, avoid using any T or 90-degree angle connections due to potential turbulence and additional static pressure generated. As I mentioned earlier, having an unbalanced system can also create duct design issues. When customers add new equipment to an existing system, they often don't consider the impact it has on the existing filtration system. In most cases, existing systems aren't modified to accommodate the additional airflow or static needs, and thus it becomes unbalanced. Lucky if you know a customer is going to expand their process on the front end. That way, you don't have to sacrifice performance if they add equipment later on. Give us a thumbs up if you've ever designed a system only to find out later that the customer's changed it and has affected something during that process.
All right. Looks like the thumbs are coming in. Well, a couple coming here. Looks like this has happened often.
Unfortunately, I've seen all this too many times in the past myself. Okay, our next system component is the dust collector itself. The main objective of a dust collector is to deliver sufficient efficiency while operating in a predictable, stable, and economic fashion. The most common mistakes or things that could go wrong include wrong filtration technology, incorrectly sized collector, either too aggressive or too conservative, or poor installation. There are 5 basic types of media collectors: baghouse, cartridge, power core, mist, and fume. Baghouse collectors have been around for over 100 years. Our baghouses use anywhere from 6 to more than 900 felt or pleated bags to filter the dirty air. They are typically the best choice for high dust loads, and they are also the most forgiving in challenging dust types. The big downfalls of baghouse collectors are they tend to be large in size and very labor intensive during filter changeouts. If you know that a bag collector is the best solution for your customers' needs, then it's a matter of determining which one to specify. It's important to work with an expert who can help you in this process. Baghouse collectors use bag filters. The 2 main construction types are fabric and pleated. Fabric bags are installed over metal cages. During filter changeout, the entire bag and cage are removed from the collector. The used filter bag is then removed from the cage and the new one installed in its place. Finally, it then goes back into the collector. Now imagine doing this process over and over a few hundred times. Pleated bags are a one-piece design. They tend to be shorter in length and take significantly less time to change out. Keep in mind that not all bag houses can use pleated bags, but if you can use them, they are a great option for certain applications, such as abrasive dust. There are a lot of options to choose from when it comes to fabric bag medias. These are just a few. So work with an expert who can help you determine which is specific for your project. For example, a polyester filter may be the great option for wood dust, but if the dust is sticky and the process generates static like sugar, I would recommend an anti-static oleophobic media, or the customer is going to have issues. The same thing goes with a one-piece pleated bag. Lots of options to choose from depending on the application. For example, if it's a high heat application over 250 degrees Fahrenheit, there are only certain specialized medias that will work effectively. For those of you new to dust collection, we thought it'd be helpful to show you a few examples. The RF bag houses on the left are used in a kitchen and bath manufacturing facility, and the one on the right is at a grain process facility. As you can see, bag houses can be very large. These are RP bag houses at an onion process facility and a skateboard manufacturing plant. This particular type of bag house is shorter and is designed to be used with pleated bags. And here are a few different Dalmatic bag house examples. We like to call them our problem solver collector because it's great for really challenging dusts like those found in rock crushing and coal processing facilities. The next type of collector is a cartridge collector, which we introduced in the 1970s. And since then, it has come a long way in its design. A high percentage of collectors sold in the marketplace today are cartridge collectors due to their smaller size and lower initial cost. And compared to traditional bag houses, the filters are much faster and easier to change out. They are best for low to medium dust loads, as well as fine, uniform dry dust types, such as those found in industries like fabricated metals, pharmaceuticals, and food processing. Cartridge collectors use cartridge filters. They come in various sizes, shapes, depending on the type of collector. There are many different types of media to use for different applications. These are just a few of ours. Again, it's important to specify the right one that will work for your customer. Power core are typically significantly smaller than traditional filter units, and thus they can fit into some pretty tight spaces. This picture shows actually 8 different power core bin vent units at a ship loading facility. There are a lot of options when it comes to fume collection. Here are a few examples of portable fume collectors for occasional welding, ceiling mounting collectors, and tower style collectors. So if there is limited to no floor space available, or if you have overhead cranes that don't allow you to use any ductwork, you still have options available. Here's an example of a large central weld fume collector. It is located outdoors, but it is attached inside to welding booths and extraction arms. Our last type of collector is a mist collector. It is designed to capture fine droplets in the airstream. It can be mounted in different ways: floor, machine, ceiling, and configured to handle one machine per collector or several. Just a quick note, we actually just did a webinar on mist collection. So if you want to learn more about it, make sure to watch the recording on our website. We'll post the link in the chat box. When I'm designing a system, the very last thing I do after completing all airflow calculations is to properly select and size the right fan. The fan is the heart and soul of a local exhaust ventilation system. It has two important responsibilities. First of all, a fan must deliver the necessary volumetric flow at a required static pressure to drive the operational system of the system. Since collectors will operate with clean or dirty filters, the required airflow must be maintained over a range of performing static pressures. Secondly, the fan you select should be able to deliver the desired static and airflow with appropriate energy efficiency and at acceptable sound level. Fan challenges generally fall into two categories: poor fan selection and poor fan installation. Static pressure is the resistance of airflow one must overcome due to system components. It's expressed in the USA as inches of water column or water gauge. When we design a system, we calculate the total system static pressure so we can size the fan properly. And here's an example. The hoods total 1.5 inches of water gauge. The ductwork, including straight runs of duct, elbows, and branch entries, total 3.5 inches of water gauge. The filters in the collector at filter changeout total 6 inches of water column. The filter to the fan ducting is about 1 inch. So the total system static pressure for this particular project was 12 inches of water gauge. Fans are sized based on system total static pressure and required airflow. Let's say that I need to size a fan for the example I gave you, 12 inches of total water column, and at an airflow of 9,000 CFM. We use the system static pressure of 12 inches water gauge and line it up with the airflow of 9,000 CFM. And when we line those two factors up, we land in between a toward backward incline, or TBI, of 25 horsepower and TBI 30 horsepower fan. So we go to the curve on the right of where we land. Since it's rare to land on the curve, and in this case, I would select a 30 horsepower TBI fan to be conservative. Please remember, you can always damper or reduce down a fan performance, but you can never damper one up. I hope you can see how static pressure is so important. A required airflow of 9,000 CFM can actually be achieved through 3 different fan sizes: a 20 horse, a 25, or a TBI 30, depending on the static pressure required to overcome. To finish things up, and then I'll open up for some questions, there are a few other design considerations to think about. The first one is the total cost of ownership for a dust collection system. How much energy is required to operate it? Where is the unit coming from? How easy is it to get parts? How long do filters last? How easy is it to change out filters or maintain the system? And what is the overall life expectancy of the system? Another consideration I want you to discuss with you is how technology is being used to monitor dust collection systems in the field. We've all seen smart technology being all around us these days, from our TVs to our toasters. Donaldson has developed a device called iQ to make dust collectors smart. This device gathers important data in real time, creates automatic alerts and historic reports. Basic service is available to customers at no charge. It's a great way to have them manage and track regulatory compliance information and troubleshoot dust collectors' issues more efficiently. And finally, the last topic is regulatory considerations, everyone's favorite. Each of these agencies may have design expectations to reduce process-related hazards. And as we all know, unfortunately, they're not always consistent with each other. Knowing the hazards will enable you and your customer to make some of the most critical design decisions up front in the process. It can be very expensive and time-consuming to change the design once the equipment is installed and in operation. Designing dust collection systems can be complicated, and there's a lot that goes into them. But just remember that that's why we're here, for you. We've sold countless of dust collection systems around the world, and we have local support in your market. And we're here to help.
Thank you, Jack. We're going to finish up with some Q&A. You can turn your camera back on, Jack. Just a heads up for everyone who's all attended, you will receive an email that includes your PDH credit. I also put a link in the chat where the recorded version will be there. If you have any additional questions, my contact information is on the screen. And then if you want to schedule an in-person lunch and learn or a customized webinar for your team, you can actually fill that out on the webinar page that I posted. All right, Jack, for our first question here, it says, is capture velocity at the face inlet of the hood or at the point of dust generation?
Yes, capture velocity is the speed of the airstream trying to influence that contaminant to get into the duct system. There's many components that come into play on that depending on the application, such as is the particles or contaminant being generated off of a piece of equipment that's causing an increase of speed that has to be overcome, in which case you have to take that in consideration in your design.
Okay. Next one here we have is, this is a three-part question, so I'll ask the first one. What accessories do you typically suggest for adjusting the air flow rate in the raw, dusty air side of the system?
Well, typically, most customers are going to a variable speed drive that has automatic or real-time feedback of that airspeed. Once it's balanced, then it's adjusted as the filters get loaded up. With the VFD drive costs going down dramatically with technology, customers are looking at that as the best solution going forward for, let's say, anything 15 horse and above. Otherwise, typically customers tend to go towards the old manual damper. Unfortunately, those are not the most reliable in the field because that requires customers to constantly monitor and adjust that mechanical damper.
So the second two parts is, do you often see silencers used on the dusty air side? And then do you recommend any specific fire dampers on the dusty air side?
Okay. I'm not sure what that question's about. Typically, fans in our systems are typically on the clean air side. So the fan and silencers are on the clean air side of the exhaust. They're not typically on the dirtier side. Those would be typically with a material handling fan, which are noisy just by their characteristics. So that's not totally something we see out in the industry on the dirtier side. It's usually on the cleaner side. But yes, we do see them being used. Keep in mind that That deals with the noise of the airstream. It does not address the actual noise of the fan motor. And as we all know in the field, or most know in the field, that acoustics are a funny thing. They can be influenced by a lot of things out into the environment.
Next one here is, are there any applications that is common to return air back into the room from the dust collector exhaust, or is it mostly exhausted out?
Well, depending on where you're located, I'm actually in the northern part of the United States, and my customers tend to want to return the air back into the environment somewhere. Due to the fact is that the cost to condition that air in the wintertime is very expensive, and if it's conditioned in the summertime, that's also an additional cost. So they try to return the air back in. The concerns would be on that, of course, is if the dust is explosive, you have to deal with mitigation on the cleaner side, which can be done. Also, if there's any kind of off-gassing in the actual airstream itself, that becomes a concern, and many times the customers do not want to return that back in because the cost to do so would be either through a absorption process or through oxidation process, which is very expensive. So if it has any kind of off-gassing, a lot of customers do what's called solution by dilution. They put a stack that's high enough that meets regulatory concerns, and they're able to exhaust that out into the environment.
All right. The next question here is, what type of collector is recommended for a plexiglass cutting shop?
Depending on what the material is off of that plexiglass cutting, you can get strings, again, depending on the actual manufacturing process. So it's difficult to say that it's going to be one size fits all. If the particles typically are less than, let's say, a quarter inch to maybe a half inch, you can get away with a fabric type of media, and potentially a cartridge style. But with plexiglass, you're going to have some static concerns to deal with, because it's going to be going through some ductwork, and then it'll be generating static, which will have to be dealt with in a grounding situation. Otherwise, if it's long, stringy stuff, boy, I'd stay away from any kind of downflow filter. I'd go with a potentially cyclone or a baghouse that can drop it out. So be careful on that one.
The next one is, do the mist collectors recirculate the air back into the space, or are they supplied with a HEPA filter?
Depending on the droplets, you can use a HEPA filter. I tend to go with a DOP as an after filter over a HEPA filter, because HEPA filters are cellulose based, and they don't like to see any kind of moisture because of the swelling properties of cellulose fibers. So I go towards if you need a polishing filter, I go with a DOP after filter over a HEPA filter. In some cases, our mist collectors have high efficiency, and we can capture that mist down to a 0.5 micron and lower on the primary stage, that we don't necessarily need a polishing filter. Again, depends on the application. There's another thing that comes in play with mist collection, depending on the application too, is hydrocarbons, and that also has to be a concern to deal with if it's important in that process.
All right. Curious to know if there is a configuration used for silica dust collection in confined spaces.
Okay, can you read that one more time?
Yep, sorry. Curious to know if there is a configuration used for silica dust collection in confined spaces.
Okay, that's going to be difficult to answer in one thing without having more information. Silica dust is a concern, as most of us know, because of silicosis. So you want to have a very effective capture, if at all possible, at the point of generation. Sometimes that's not possible, depending on the application. So you want to try to use, if you're using like a backdraft hood or anything like that, you want to use a high velocity to keep that air stream from getting in contact with individuals. Many times when you're dealing with silica, that will require monitoring to be done. So that you have to take in consideration.
Okay.
Again, if you want to, on that individual question, if you want to reach out to us, we can get into more details on that. It's difficult to address without having more information, just being honest.
All right. Due to the energy conservation, sorry, I just butchered that. Okay. Due to the energy conservation requirements by a lot of clients, There is an increasing requirement for recirculating air. Touch on that. I kind of think you did already, but do you have anything else on that? Bringing back the air.
Yeah, I think energy, like we talked about in a couple of the questions I answered earlier, there are various things to consider. Yes, if you can recirculate the air at all possible in conditioned, or I should say in non-temperate areas, that would be the most operative or most favorable if you can do that. But again, consider the airstream and making sure there's no off-gassing involved and things like that. And if the dust is explosive or flammable, to address that with proper mitigation. And like I said earlier, that many of my customers and the industry are going towards VFD driven fans with real-time monitoring, like differential pressure gate monitoring tied into a VFD, so they can get to that monitored real time.
All right, next one here is raw cobalt materials for battery production. What dust collection system? Any explosive device requirements?
Okay, depends on the operation. That material can be combustible. You have to take that consideration along with the actual process. I would lean towards, if you can, go with a cartridge style collector in that application, because that tends to be very fine dust particles, typically dry, that lends itself into a cartridge style. I'd go with a downflow design over an upflow design for cartridge, due to the fact is this stuff's very fine and you don't want to have too high a can velocity or filtration velocity to cause reentrainment of the dust.
All right. Any concerns with metal grinding systems using portable dust collectors? Is there an explosion risk?
The answer is, in short, yes, it can be. Depending on the metals, you don't want to have what's called a rocket car in a facility. I'm not going to mention the customer's name, but I've seen the results of using a dust collector improperly in combustible metals that took out a wall about 100 feet away. Luckily, there was no personnel between the wall and that dust collector when it did move at high speed. So yes, it can be a concern. Be careful on any application that you're dealing with filtration to try to get an understanding of the dust. And if there's a DHA, which dust hazardness analysis, which is supposed to be done by all customers in the United States, and I'm sure all around the world, that you have dust that is non-combustible. In welding applications, where most of these are at, that tends to be an iron oxide, which normally is not combustible, but again, you really need to do your homework on that stuff, because we live in a litigious world.
And just because you're just now talking about that DHA, one of the questions says, if a client is not super technical and not willing to do the dust hazard testing, what resources do you use as a rule of thumb?
Well, that's a good question. You have to be very careful on your answer, because again, it's a litigious world. So you may want to make sure, well, you definitely have to make sure the customers work with an AHJ if the dust is deemed to potentially be combustible, because you and your customer are not AHJ's authority having jurisdiction. There's 4 entities that I'm aware of in the United States that could be potentially classified as such. So having said that, you want to make sure that they're on board with whatever solution is proposed, because that's all you can do is provide potential solutions. And if the AHJ agrees, then you can fall to potentially, again, I'm using the word potentially, looking at a chart and saying, okay, your dust has this. And if you look at the online chart, it has a KST value. KST value is a 3-letter, an acronym or abbreviation for a long German word that I took 10 years of German, I can't even pronounce. But it's a scale from 0 to about 500. The higher the level, more likely it'll be of metal dust. But in the United States, anything above 0, no matter what, is considered combustible. So again, be careful on that. Work with an AHJ that's involved in that process. And if there's any whiff or concern that you have on combustible dust, please treat it with kid gloves and be very concerned on a solution. Again, make sure that you let the customer know that you are not an AHJ, but you're willing to help them in the process. And if not, reach out to us. I come across that quite a bit, usually on a weekly basis.
All right, next one is, are you using duct pressure sensors to run the fan VFDs? If so, how do you keep them clean?
That is a good question. Answer is you have to be very careful on the dust that you use. I typically use a type of pitot tube that is not directly, how can I say it? It's in the airstream, but it's not in the airstream too far to cause any kind of clogging. If you are using that type of instrumentation for feedback, be very careful on making sure that's cleaned. Otherwise, there are airflow controllers out there. We happen to have one too that uses a factor in its performance. So it'll say that, okay, we'll ramp up roughly the VFD to be in a envelope style or envelope window to operate in that potential pressure drop on the filter elements. So it doesn't have a exact probe inside the ductwork.
All right, next one is, when is the air to media or air to cloth ratio not the correct parameter to use?
If there is no filter media inside or being used, such as a cyclone. But for the most cases, if you're using a filter of any type, you should always consider air to media ratio or air to cloth or AMR. It's very important. And keep in mind that all applications and the type of media being used are different. So just because you're using one that you used in the past for, let's say, grinding of steel dust, and now you have one of wood dust, it's not the same AMR. So there are considerations to take into account. And if you reached out to an expert or someone that's very experienced, they should be able to help you in that. So it's the application, it's the type of collector, it's the type of media used, but you do need to keep that AMR in consideration whenever you're choosing a filter element.
Right. What are the dust considerations for an angle of repose of big house hoppers?
Okay, one more time, please.
What are the design considerations for the angle of repose of big house hoppers?
Okay, I assume they're referring to bridging, and if not, please respond back. So the concern is what type of material that you're collecting, and is it dropping out? Yes, you want to consider using potentially steep hoppers if the material is wet or is conglomerative. So if it's hygroscopic, absorbs water, or is wet, let's say you're dealing with wood processing that has a lot of green wood, which tends to have a lot of moisture in it, and or it has is conglomerative, that it sticks together, then you typically want to use a steep hopper to consider in your discharge of your captured dust. And whatever you have underneath that hopper to make sure you're not bridging, so you have a rotary airlock that's large enough. If you can use a rotary airlock, if the dust is not combustible, you could look at a double dump application too. But that will be also a part of the consideration when choosing the angle of the hopper.
All right. What is the smallest dust collector Donaldson makes looking for a small skateboard shop?
Well, it depends on the application, and again, depends on the material being captured. We make ones that are a few hundred CFM to less than even that. But with skateboard shops, you may be dealing with composite material, you may be dealing with wood, and if that's the case, then you have an explosive dust issues. And one of the things that I'm not going to get into too much in the weeds, but be careful on that. Everyone says, well, it says that in NFPA that if you use a 55-gallon drum or less size dust collector, you don't need explosion venting. That's not true. That has to do only with 55-gallon drums dust storage. You still could have a blast radius with a dust collector that's very small. So don't think that gets you out of the woods.
Which orientation is effective, vertical or horizontal filters?
Depends on the application. So we make both. We make vertical and we make horizontal filter orientation. Depending on the fine dust, typically horizontal is the best way to go, if at all possible. If it's super heavy, you may want to go with a vertical style. Again, it depends on the application. So there's not a one size fits all. We make all the above.
All right. It says we have an application for chicken feed vitamins and mineral mix that has high formaldehyde emissions from one of the components. Are there special considerations for formaldehyde?
Yes, so formaldehyde can cause issues over depending on what you're going to do with that airstream. So first of all, you have to be concerned about the seals. Over time, that formaldehyde could attack the seals in the dust collector, and those seals could be related to the doors of the filter unit. They could be related to the filter elements themselves having a kind of sealing element that could attack that material over time. So you have to be careful on the airstream. And again, we talked a little bit about chemical composition of the airstream and how that could attack different things. Well, that would be one, sealing. Then if you're returning the air, it's a concern that I don't know if you want to do because of that off-gassing. Obviously, the concentration level would be an issue. Probably would not return the air back into the work environment, and then you'd have to look at a solution for that so-called filtered air and what you're going to do with it.
All right. This one's another one on DHA. So is a DHA required by code?
If you look at NFPA, yes, it is. And I can't remember the exact standard on that. I apologize, guys, but there's a standard that deals with that. All in the United States, all customers need to have a DHA, if at all possible, perform. Now, there are customers that are contract packagers, and so they could have hundreds of different variations. That's when you'll have to work with your AHJ on to determine what would be acceptable. They may fall back and say, well, you have so many of them that we'll just go off of the worst case scenario, in which case, whatever they find is the highest KST value in that process, they might just default to that.
All right. It says, how do you approach and balance a system you don't have details of the design?
What's the last word?
When you don't have the details of the design, how do you approach the balance of the system?
Well, that's a difficult question to ask. An answer, I should say. Not maybe ask, but answer. You really can't. You need details to be able to balance it. I don't know how you could do that and give it a good answer. You could say that, you need to have certain airflows in that system to be maintained. But if the customer or the people involved in it are not giving it information or not able to determine that, I don't know if I'd be confident in going forward on something and saying, yes, I can guarantee this performance.
All right. And it says, does the FPM discussed apply to all types of materials such as soybean, corn, flour, sugar dust, etc., specifically in the return to the dust collector dust piping?
Yeah, what was the first part of that question?
Does the feet per minute discussed apply to all the types of material?
Okay, feet per minute or transport velocity or conveying velocity, as we discussed, is important, especially if you're dealing with those materials that you mentioned, because they can be considered combustible. So you don't want to have any dropout of material in that ductwork. So yes, that feet per minute is critical. And again, depending on the material, it's more critical when you're dealing with combustible or flammable material to make sure that you have a certain maintained velocity. And an AHJ would be involved in that process because you did mention some combustible dust in that question.
Okay, the last questions I'm going to try to get because some of it's doesn't make sense. It says titanium dust in paint powder factories like Juten. When used, I found the filter gets blocked faster than usual and it looks clean in the same time. So the question is, do we use a DFO or DFE type? Do you have a solution?
Okay, well, one of the key words you mentioned in that question is titanium dust. And titanium dust by itself is highly combustible. I talked a little bit about the KST value, which again is that an acronym for a large scale from 0 to like 500. Titanium would be in the higher level if by itself. So if there is a combustible nature to that, you have to make sure the AHA is comfortable with letting you use a filter element for that application. If they are, then with the right mitigation, again, considering that it's potentially over 0 on combustibility, I would go towards a DFE over a DFO just because you have that extra dropout internally in the filter unit to create more separation of the dust.
All right, Jack, we got through them all. Congratulations, thank you for all that. Thank everybody for joining and asking questions. It was a lot of fun. And like I said, my contact information is on the screen. If you do have questions on specific applications or projects, we have territory managers across the United States that are willing to help with any design. Thank you.